Hi there, Scott again from EdgeMath. Let's see, had another question from a student about Prim's algorithm and minimal spanning trees. So maybe a basic idea. So say we've got a map of the U.S. with the flying distances between major cities. I just made these up. These aren't exact, but just as an example. And say we want to find a way to connect all these, like maybe we've got uh, an airline that it's going to base itself out of each city, but it wants to be able to connect to each city, but not necessarily fly all the routes. And we want to know if there's a way to do that, a way to organize the routes so that the total distance is the smallest. So again, the airline is going to be based at each of these cities. It's going to operate from the airport, but it won't necessarily fly all the routes, but it needs to be able to connect to all the cities. And we want to know if there's a way to do that so that the total distance of its routes is the smallest. And there is a way to do that, or two ways. One is Prim's algorithm. So I'll show you Prim's algorithm. So what we do is we pick any one, pick any vertex. In this case, cities, airports. So let's say we can pick Chicago. So let's pick Chicago. Let's do that in red. And now we want to, so once we've got this 2, let's do that in black, 2, find the smallest edge that is currently connected to a vertex we have added and that doesn't not lead to a cycle. So basically we're gonna start with this vertex and just start adding edges, adding the smallest edge we can find that's connected to it, but make sure that the edge connects to a new city, i.e. it doesn't create a cycle or a redundant, it doesn't give an extra city, or an extra way to a city. So let's see. So we can, from Chicago, we've got 500, 700, 1,000, 2,100. So we'll add this 500 to Atlanta. Now we look at all the edges connected to, we've got Chicago or Atlanta. So we're going to look at all of these edges and find the smallest one. So we've got 800, 900, 2,500, 700, 1,000, 2,100. Out of all those, it's like 700 is the smallest. So we add that vertex. That's Chicago to New York. And then, so we've got Chicago, New York, Atlanta. Let's see, are there any? Let's see, we've got 800. So we look at all the edges attached to any of these. We've got 200, New York to Boston, 1,000, 2,100, 2,500, 800. But notice, let's see, if we connect New York and ATL, that would give us a cycle. So we can't do that. Or we have 900 from ATL to Boston. So out of all of those, it looks like New York to Boston is the smallest. So we add that. And let's see. So we've got, we added Boston. So we've got, that connects to Seattle, that's 2,900. We've got Boston to ATL, that's 900. But that would create if we added Boston to ATL, that would create a cycle. So we can't do that. And then New York to ATL is 800. That would create a cycle too. So Chicago to Denver, 1,000. Chicago to LA, 2,100. ATL to LA, 2,500. So it looks like this 1,000 edge is the smallest. So Chicago to Denver. So again, it's larger than New York to LA or Boston to, or sorry, New York to ATL or Boston to ATL, but these are both smaller, but they would create a cycle if we added those edges. So got Denver now. Let's see, Denver to LA, that's 1200. Denver to Seattle, 1500. Chicago to LA, 2100. ATL to LA, 2500. Boston to Seattle, 2900. Boston to LA and New York to ATL. Those are both relatively small, but they would create a cycle. They don't go somewhere new, so we don't add those. So it looks like Denver to LA is the smallest. And now we do, let's see. So we've got almost all the cities. We just need to connect to Seattle. So we look at all the. So again, we look at all the edges that are connected to any vertex in the graph. So 2100 LA to Chicago. That would create a cycle. We can't add that. LA to ATL, 2500. That would create a cycle. These two would create cycles. Boston to Seattle is 2900. Denver to Seattle, 1500. LA to Seattle, 1000. So we have that. 1000 is the smallest. So, and then now we've got all the cities. So three. So we change the color. We would stop once we have added all. Once we have all the vertices in our minimal spanning tree. And then so for this one, we've got all the cities connected. So if we tell the airline to fly these routes, they'll be able to get anywhere up to these airports. And then the total distance of this, minimal spanning tree. So minimal in the sense that there's no other way we could organize routes that has a smaller total distance. So this total distance there is, let's see, 1000 plus 1200 plus 1000 plus 500 plus 700 plus 200. Maybe you have a calculator, but that gives us 237, 44, 4600. I'm getting 4600 miles. So we would tell if we were designing this for the airlines, we would tell them to fly these routes. I'll show another example of how we can solve this in a next video, but this is Prim's algorithm. So remember, we just pick an edge to start at, or pick a vertex, then we start adding edges, and from the smallest to biggest. So we look at edges that are already connected to a vertex in the graph, and then we add those until we've got every vertex. We make sure we don't add any cycles along the way. So great. If you have any questions, let me know. Otherwise, hope you have a great day. Goodbye.